Well, good morning. This is 9:33 on Monday, the 13th of March, 2017. It was supposed to be Calculus 1 class, Math 125. Right now, I'm the only one in the room, so I'll go on and get started from where we left off last time. Normally, I'd ask if there are any questions, but with no one in the room, that's sort of a moot point. So let's get the slideshow set up from where we were. Okay, I think this is the slide from example 2. Okay, but example 3 doesn't have a slide, so we'll use the white space around this one to work. Let's just see if there's a nope. Doesn't get any better moving backwards. All right, example 3. This is chapter 3, differentiation. 3.5 higher derivatives. Example 3 says, calculate the first 4 derivatives of y is equal to x to the minus 1. Let me get my pen activated for the darker color. Okay, y is equal to x to the minus 1. Now this is the form that I would use to take derivatives. But just as a reminder, what we're talking about is that it's the same as the function 1 over x. But please don't use 1 over x. Easier to use the powers, so write this as x to the minus 1. Okay? Well, what's the first derivative? Y prime would then be minus 1 times x. That's minus x to the minus 2. Because you multiply the exponent by the coefficient. Negative 1 times 1 is minus 1 times the variable to the minus 1 power. Okay, so it's minus 1 would be minus 2. Y double prime would then be minus 2 times minus 1 is positive 2, x to the minus 3. You drop the exponent by 1. Y triple prime would be minus 6, x to the minus 4. Okay? Now, if you recall, anything past 3, we don't just keep putting primes there. They get really messy, hard to read. Usually people don't go past triple primes. So, what we do now is y to the 4th. When you put the number in parentheses as a superscript, that means, and it's a function underneath it, that means it's the 4th derivative of y, and this would be 24 x to the minus 5th. Okay? Now, I was multiplying out. In the book, they were fairly clever to do this. This would be a minus 1 times x to the minus 2. This would be a positive, let's do the same, 1 times 2 times x to the minus 3. This one would be a minus 2 times 3, or you could say 1 times 2 times 3 to x to the minus 4. And this one would have been 1 times 2 times 3 times 4. 6 times 4 is 24, x to the minus 5. Now, what was the advantage of writing them that way? They were a lot longer to write. That's a disadvantage. But the advantage, it lets you see a pattern. And the pattern is that every other power changes sign. So you might say the 0th derivative was positive, first derivative was negative, second derivative was positive, third derivative was negative, fourth derivative positive, fifth derivative will be negative. So y to the n, and put that in parentheses because that doesn't mean y raised to that power. The nth derivative of y would then be n, whatever power that is. The 4th is even, the 4th is positive, 2nd is positive, 6th is positive. So this will be sorry, let me go back. It's not what I really want to do with the n. Here's what I want to do with it. Minus 1 to the nth power. If n is an odd number, that's going to be negative. If n is an even number, it's going to be a plus 1. Okay? And then, I don't know if you've run into this notation before. Notice this was a 1, 1 times 2, 1 times 2 times 3, 1 times 2 times 3 times 4. Next one is going to be times 5. Next one by 6. Next one by 7. So basically, what that is called is n factorial. Okay? Is when you count downward from if n is 7, that would be 7 times 6 times 5 times 4 times 3 times 2 times 1. Of course, we usually leave off the 1. I wrote them in there for effect. That really doesn't contribute anything. It doesn't change the product any. I wrote them in to show you are counting every term. So that's n factorial, and that would be x to the minus n plus 1. Okay? Because the nth factorial, the nth derivative would always be one more power. See, 0th derivative minus 1, first derivative minus 2, second derivative minus 3, third derivative minus 4, fourth derivative minus 5, and so on. So it'd be minus n plus 1. Okay. Now, they wrote the same thing, but they did this, let me make sure that, yeah. They did minus 1 to the n factorial, that's your coefficient, and then the variable x to, they wrote it as minus n minus 1, which is fine. I think minus n plus 1 in parentheses makes it a little easier to see, but that indeed is the same. If you distribute the minus sign here across the parentheses, you get n minus n minus 1. All right, done. Reminder, the n factorial is the number that is starting with n, multiplies by each factor, counts down by 1 until you get to 1. Okay, so here's a little definition. 1 factorial is 1. And here's another one. 0 factorial is also 1. And that's why we could say this is 0 factorial, which is 1, x to the minus 1. Okay? 3 factorial is 6, and so on. Okay. Now, it's not always possible to find the simple formula for the higher derivatives of a function. In most cases, they become increasingly complicated, so don't look for them. This one just happened to be one. The simple power function, that was easy to do when you had a negative power. All right, let's move on to example 4. I don't think this has a figure either, so we'll write on same slide again. Calculate the first 3 derivatives of this. F of x is equal to x e to the x. Okay? Now, my question to you, if anyone were in the room, I'd be asking you and expecting an answer on this one. What rule are we going to need to use to find the derivatives of this? And hopefully I hear all the voices answering me product rule, because this is a product of 2 functions. Okay? So how would that work? F prime of x. All right. Now, you can do this either way you want to. I'm going to do it one way. I bet you the book will do it the other. We're almost always opposite each other. And do I have a student coming in? Please say yes. Yes! Wow! Thank you so much. I was beginning to doubt my sanity talking to myself. Okay. Well, it's in doubt anyway, I heard you say under your breath. Okay. So, lights and also projector. Take just a moment to get fired up. All And there weren't any major announcements this week that I know of. If my memory's right, I've got to go back and check my emails. They moved it once, so I think the faculty meeting is scheduled for Thursday. I believe that's correct. I've got to check my emails. It won't affect this class any, and it won't affect office hours any because it meets while I'm teaching my class. So, but if you do see or hear people talk about that, for me and my classes, it doesn't have an influence. Since the Thursday class it impacts is a mini-term class, I can't afford to be there, so I've got to request permission to miss the faculty meeting, which somehow I guess I'll get over. Okay, so yeah, into little bitty pieces. Okay, we're doing example 4. I just did example 3, and we're just starting example 4 on page 152, section 3.5. And I did ask, but you weren't here to answer, so I'll ask again, what rule do we use to take the first root?
It's not the chain rule, what's the...
No, we're not. We haven't done the chain rules yet. You're cheating. Okay.
Is it the limit law?
No, we're not going to go back to limits for... If you want to, I guess we can.
No.
But, okay,
Please
right.
Please don't.
Yeah.
I just can't remember the name of it.
Well, that is... What does it mean? X e to the x.
It's just e to the x.
Well, here's a function, there's a function.
You're multiplying them together.
Okay, so therefore, what's the answer in a multiplication problem?
The sum.
Oh, that's adding.
Product.
The product rule, yes, the product rule. Okay. It's like when I was driving yesterday, there was a dumb quiz show on. I'd never heard this before. It was, the quiz show is, what?
Wait, don't tell me.
Yes.
Yeah, I listen to it all the time on NPR.
No. Huh?
On National Public Radio.
Yeah, exactly.
Alabama Public Radio. Wait, don't tell me.
It was either that one or Says You. I think it was Says You.
Okay.
Okay, but you've heard that one too.
Yes.
Right? It was baseball terms.
Mm-hmm.
And they came up with a weird definition, and you were supposed to come up with the baseball term that fit that definition. Did you hear that one?
Yes, I sure did.
And what was let's see. Let me see if I can remember it now. A chamber pot.
Yes.
Yes.
That was it. It's just, and what's so cool is that they just get the most random, definite,
Yeah. And that was what? You remember? What baseball term?
Was it was it helmet or something?
No,
it was,
Think bullpen.
might have been dugout or something.
No.
No.
Someone guessed that.
Yeah.
Think of bullpen. Who is it that warms up in the bullpen?
Oh, like the pitcher or something?
Which one do they call him? Coming in for the guy who started or for the guy who's in the game?
Yeah, gosh, the substitute pitcher or something like that. It's
Relief pitcher.
Relief pitcher, that's it.
So a chamber pot would be relief pitcher, right? Okay.
Yeah.
Never mind.
That's right.
But that's sort of what we have here. Product rule. Okay. What does that have to do with chamber pot or relief pitchers? Okay. I felt like I was giving you clues for it. That's what it was.
There we go.
Okay. So how do we find what does the product rule tell us to do with these two functions?
To
Take the derivative.
yes.
Yeah. What does it? How do you do it? What's the rule?
Is it loading high and low?
Okay, that's quotient rule.
Okay.
It's kind of like that, only simpler.
Oh, it's loading high. No, it's
There's no lows and highs, right?
It's just
Those are denominators and
the
numerators.
derivative of the first times the second.
Got it.
Yeah. Okay.
So what would that be then in this case?
1
Right?
times e to the x.
Right.
Just e to the x, and then this, so e to the x again.
Plus.
Plus e to the x.
The first time.
X. Yeah.
First times, yeah, x times e to the x.
Yep.
You got it. Okay. Now, it said find the first three derivatives. We're doing upper derivatives, right? Higher derivatives. And the problem example 4 says calculate the first three derivatives of this. We got the first one. What's the second one? E to the x. Got it.
Plus e to the x.
E to the x. Got it.
And then you have to do it again. So the e to the x plus e no x e to the x. Okay.
Okay. I mean, think about this. It's this one, and then we
And
take
then
derivative
you
of
just
that.
bring
It's
that
exactly
straight
that
back.
again, right?
Okay.
Right.
Gotcha.
Okay. So simplify that a little bit.
So 2e to the x
2e to the x plus x e to the x. Okay? All right. F triple prime.
So 3e to the x.
Okay.
Sorry, I just
Yeah, you did it. Fine. 3e to the x.
Plus x e to the x.
Got it. You picked up on the pattern really nicely there. Because it's 2e to the x plus e to the x plus x e to the x. Absolutely. Okay? And frankly, I think that's why you did as well as you did, which was pretty good in the math team, because the patterns, you see them and adapt to them pretty quickly. And way to go about that. If I hadn't told you that already, that was very nice. Okay, so here is another rule then. What would be the nth derivative? And anytime it's past 3, we put the derivative in parentheses, if that's a function there, of that function.
So would you say
n e to the x
plus x e to the x?
That's it.
Okay. Because that's the only number that's
That's the
changing
only
that.
number that shows up there. Exactly. Okay? So it's n. Okay. They found another way to write it. Okay? Here's the other way. Factor out the e to the x. And then you have what?
You just have n plus x.
So there's yet another way to write it. Okay? Only they wrote the e to n plus x in front, e to the x. Okay? But yours was perfectly fine too. I don't know if one's preferable to the other, but yeah. All right. The next example is one they do have a figure for. So we'll get the picture here. And this is acceleration due to gravity, a really applied problem here. Find the acceleration a of t of a ball tossed vertically in the air. To me, that should be into the air, okay, from ground level with an initial velocity of 12 meters per second. How does a of t describe the change of the ball's velocity as it rises and falls? Okay? Now, they're requiring you to go back and use something they'd already given you, which was, they called it, I think, Galileo's formula or something like that. Remember, we had it. Yeah, you've had physics too.
It shows them on top of the leaning tower.
Right.
All the, yeah.
Right. So S of t, okay. So the ball's height at time t, S of t is equal to, do you remember what the formula looks like? It's at the top of the next page. Page 3. Page 153. Next page. No.
This one.
That one, yeah. Very top.
Like I said, my looks a little different.
Oh, that's right. That's right.
I think I found is S of t equals
Yes.
S0
S0.
plus v
Not.
sub 0 t
Yeah.
minus 4.9 t squared, which is the acceleration due to gravity.
Half of it.
Half of it.
Right. Okay. Because it's 1/2 at t
Instead
squared.
of 9.6, right? Or
Right.
9.8.
So you already got the answer, whether you realize it or not. But that's your Galileo's formula for acceleration. I think that's what the book called it, for any object. Now, quite often, mathematicians being real cool, they call that S naught and V naught.
S naught, okay.
Yeah, you'll hear them say that. It is a sub-zero, which is nothing, you know. But you can also think of it as S sub O, which would be original. You can think of it that way too. That's how I usually do when I'm explaining. Other times in physics, it would be S sub I, meaning initial. Okay, so you see it lots of different ways. Okay, now the ball's height at time t is that by Galileo's formula. That's where they say it. Okay, and this is measured in, by the way, meters. How do you know that's meters?
Because that the time is already squared in some meters per second squared? Or?
Okay, well, you're dancing around it a little bit. It's that first thing you said.
Okay,
What is
so
this?
It's half of the, gotcha.
Of what?
Of the acceleration due to gravity.
Which is?
9.8.
What?
Meters per second squared.
Meters per second squared, that's what makes it be meters.
Gotcha.
So they gave you the acceleration in SI units, and therefore
sense.
it has to be meters.
Cool.
Therefore, this has to be meters per second. That has to be meters. Everything in meters.
Cool.
If that had been a 16 there, you'd have known it was in feet, because half of 32 feet per second squared would be 16. Right. Okay. Now, if you go back and read the problem, find the acceleration A of t of the ball tossed vertically in the air from ground level. What does that tell you about S sub 0?
0.
That's 0 because it's thrown from ground level. So you're starting at 0. Okay? With an initial velocity of 12 meters per second. Your V0 would be 12 meters per second. Initial, that's why. If we're going to call it initial, I'd rather call that V sub I. But it's okay. We can understand that. Okay. Now, so that makes our formula to be S of t is equal to 12. I'm going to leave off units for now. T minus 4.9 t squared. Okay? And it said, come up with the acceleration A of t. Well, what would be the first thing you would need to do?
Need to isolate the t's?
No. You're looking for the acceleration as a function of time. You've given displacement as a function of time. What's your next step? Take a derivative, yes. It's a good old Sunday school class, right? Okay, what would that be?
So just 12, or do you want us to rewrite it?
A little bit.
Okay, so negative.
Okay, here's what I want you to do. S prime of t is the same as what?
Okay, so now just straight down to 12.
Okay, except what is S prime of t? First derivative of displacement is physics now. Think physics. First, time rate of change of something is, of displacement is velocity. Okay? That's what the first derivative of displacement is velocity. Time rate of change of displacement is velocity. Okay? And what would that be?
So
12
minus 9.4. I know it, 9.8.
Of course, okay. I knew you knew it already. T. Okay, that's your velocity equation. And when you take the next derivative, that's S prime of t, S double prime of t, which would be V prime of t. And what is that? Yeah, but what is V prime of t? First derivative of the velocity is the
displacement. No, it's
what's the question looking for?
we're looking for the initial, find the acceleration.
As A of t. That's it exactly. The
velocity, then accelerate. That's right.
Yes. First derivative of velocity is acceleration, and that would be what?
Just -9.8.
Negative 9.8. And then you could put the units in if you wanted to. Meters per second squared. You know that's second squared because the t was squared that you were saying earlier, so that would give you meters. And that's what they're asking, and you said it right off the bat. It's half of 9.8. That is the acceleration due to gravity. Okay? Now, our acceleration of the ball would be the minus because it's pulling it downward. Okay? So, negative 9.8 meters per second squared. That is your A of t. Okay? As expected, the acceleration is constant with the value negative g, which is negative 9.8 meters per second squared. As the ball rises and falls, even though velocity is initially decreasing and then increasing, or speed is increasing as it's coming back down, actually the velocity is always decreasing because it's increasing downward, or decreasing upward, increasing downward. So this is your velocity graph. There is your quadratic, okay? And this would be the velocity graph, a linear function with a negative slope. And then your acceleration would just be a constant function, negative 9.8. Okay. And that's what those two graphs are there for, too. Okay. What they didn't do was graph the acceleration function, but that's a constant function, negative 9.8. Now, of course, what they did do here, if you notice, they adjusted the scale so they could fit. This is 7 units this way, and that's less than 2 units that way. But they did it to, I guess, make it pretty. But of course, they're measuring different things, so meters can be measured on different scale of time. So they don't have to be the same. And then down here, that's 12, and that's even like some water looks like there. But that's just because we started at velocity of 12, and by the time it hit the ground, its velocity was negative 12. When it was at its peak, its velocity was 0. Okay. Now, what you were tempted to do to begin with, solve for t, that would have given you the variety of things. Like if you solve this one for t, in other words, set velocity equals 0, where's the velocity equals 0? That would be obvious, something that was between the 9.8 t is equal to 12, so it's a little bit greater than 1, and sure enough, your velocity is 0 there. That's where it stops rising just before it starts falling. Velocity instantaneously there is 0. And where it hit the ground would be set that equal to 0, and then you have a quadratic to solve. Okay, this one equal to 0. Only that would be pretty easy because you can factor this 12 t times 12 minus 4.9 t. Well, obviously the first one, t is equal to 0, that's where you threw it from, okay? And you threw it up from, okay? So, the second place then would be 12 minus 4.9 t is equal to 0. 4.9 t is equal to 12. And divide that, you're a little bit greater than 2. Okay? So that's for that. Which also comes up being exactly twice this. Same distance going up as it is going down. Same time elapsed going up and down. Okay? So you see all of it works together pretty nicely. As long as you're ignoring air resistance, of course, because that would then distort your parabola somewhat. Okay. Now, sort of the next topic here. It says, can we visualize the rate represented by f double prime of t? Okay? And that's what these three figures are attempting to do. This is, I thought the other two were our graphical insight, but these are the graphical insight. Do you feel really insightful now? Of course you do. Okay. Now, I don't know exactly why they did what they did here, but I take it that this blue line here is our original parameter, which could be your displacement vector or displacement function. Okay? Now, why they made this end of this tangent line blue and that line red, I do not know. I think it's just an error, but they got it in the book that way too. Is it in your book that way too? I don't know why. Okay? But what your first derivative tells you is the slope of the tangent lines. Here's the slope is extraordinarily negative, still negative but less so. So the slope is actually increasing slightly because it's very negative, not as negative. 0, which is still increasing, somewhat positive, and even more positive. So your tangent lines are increasing the slope as you go from left to right. Okay? Okay, the tangent lines are turning. Now, if you were on up here, as you keep going up, just picture that. That's getting closer and closer to a straight line. Never is quite a straight line, but it's approaching. So up here, the tangent line's here. Next place it's there. It's not changing much at all. It is changing, but not very much. Same thing here. Very negative. A little less negative, but not much. And then a little less, a little less, a little less. And finally, then when you get down here, it starts changing very rapidly. But then it slows the change again. Okay? If you think about it, your tangent line is telling you how the function is changing. Not very much up here, not very much here. Your second derivative is then telling you how your first derivative is changing. And since the first derivative is changing very slowly here, the second derivative is going to be very, small negative, but increasing in negativity, and increasing to go to 0, and then now y. Oh, I'm sorry. I was trying to tie this to that. It's not tying very well. Okay. This is just showing the tangent lines are increasing their slope very rapidly on this one. They don't graph what that second derivative is, but what it would have to be is negative, increasing everywhere, increasing slowly, rapidly, slowly, increasing everywhere. If you did that. Large second derivative here, very small second derivative there. On this one, your first derivatives were changing much less, so your second derivative is, your first derivative is changing much less rapidly than it was here, but it is changing still, like we said, always increasing. First derivative, the slope of the tangent lines are increasing. Even when they're negative, they're increasing. So that would be an increasing second derivative, okay? But smaller throughout, okay? Here, you have a linear function. The slope is the same, a constant, so therefore the tangent line doesn't change. The second derivative, how fast is the tangent line changing? It's not changing, so that would be a 0 second derivative. To me, this could have been done probably a little bit better, but what it's saying is true. Let's go to example 6. Okay? Identify, okay. All right. Identify curves 1 and 2 in the B part there. 4 B. Yeah. As the graphs of either f prime or f double prime for the function f in 4a. Okay. First derivative would be measuring what?
let's see. I'll slow that tangent lines term.
Okay. Now you're giving me the answer for second derivative.
Okay.
The first derivative is measuring.
How rapid that they turn.
Okay. First derivative is measuring slope of the tangent line.
Okay. Right.
Okay. And what is the slope here?
It's negative increasing.
Negative. Increasing slightly. Okay. But it's negative, negative, negative. Less negative, less negative. It becomes
constant. 0.
0.
And then
Positive, slightly positive, more and more and more. So which one of those two curves would describe that slope of the tangent line? Green one or magenta 2? Whatever the color that is.
It would be the open the parabola or the downward facing parabola.
Okay. Say again what the slope of the tangent was here.
It's decreasing.
Yeah.
Negative.
Negative. Negative. Less negative. Less negative.
And then 0.
0. Positive. Positive. So the slope of the tangent line has to be negative. The green is never negative.
Okay.
Not shown there. Between A and B is
because
never
it's
negative.
incorrect. Gotcha.
Okay, the slope is negative here, 0 here, midway,
Gotcha.
and then positive after that.
Gotcha.
And
I was looking at it wrong. I was imagining it going just basically flip flop. So it was increasing positively.
okay, yeah,
and then
you're
decreasing.
thinking second derivative.
Gotcha.
It's asking first derivative.
First derivative.
Okay.
Gotcha.
All right. Good deal. We doubled our class size. Okay. By the way, I forgot to mark. No, I got you here anyway. Okay. So the top half of the alphabet is very well represented. The bottom half hasn't shown up yet. Okay. All right. And by the way, I guess I needed to say this too. I forgot to say it earlier. This class, of course, one of my best class ever, of course. So far this term, 0 papers. My only class, except my second mini-term class, which just started last week, who hasn't turned in a paper yet, okay? Hint, hint, okay? Number 2, I've had 1 test in, okay? First test. 1, uno, okay? Just 1. So please, folks, get me some work. I think I told y'all earlier that sometimes, or at least on the academic calendar, they say this week we're supposed to report midterm progress reports. In fact, that was supposed to be last week, wasn't it? And today was the last week of that. Okay. Okay, thank you. So try to get me something in. I checked again over the weekend and they hadn't opened it up yet. So I think you're in the clear that way, but don't get far behind. Like I gave my 8 o'clock class their second test this morning, and at least one of those guys hadn't turned in the first test. So don't get caught with tests piling up on you, okay? That's the disadvantage of take-home test, is that if you procrastinate a little bit, you can really get in deep trouble fast, okay? All right, so we've identified here that the pink line here, or magenta, whatever you want to call it, is the graph of our first derivative of this blue function. So, what would be, do you think the green line would be a legitimate curve of the second derivatives? Let's see. Okay, good. The second derivative is, because the first derivative is negative but increasing, the second derivative is positive, okay? And it's positive but fairly small positive numbers up here, but getting, as you get near the term, the first derivative is changing more rapidly. See, here it's not changing much at all, but here it's changing more rapidly. So the second derivative must be increasing here, but then decreasing because now the first derivative is increasing slowly again. Still positive, but increasing more slowly. So sure enough, Roman numeral 1 is a good graph of your second derivative of the blue function here. Okay. Any questions on that? Roman numeral 2 was the first derivative. Roman numeral 1 was the graph of the second derivative. Okay. That finishes, by the way, 3.5. There is a summary there, pretty short summary. But let's do the preliminary. Do y'all like to do preliminary questions?
Yes.
Whether you like to or not, we're going to. No, I didn't say that, did I? Okay. Let's do preliminary question. On September 4th, 2003, the Wall Street Journal printed the headline, "Stocks go higher though the pace of their gains slows." That was actually a headline. The stocks go higher though the pace of their gains slows. Rephrase that headline as a statement about the first and second derivatives of the stock prices, and it says, sketch a possible graph. Stocks go higher. What does that tell you?
That it's increasing.
What is increasing?
The tangent lines.
Yeah, the slope of the tangent line is positive. Okay, that's what it means. Increasing gets into the second derivative. Okay, the slope of the tangent line is positive because the stock prices are increasing. So the slope of the tangent line is positive, but the rate at which their pace of their gains slows. So the right, and what it is, the second derivative would be negative. Here, the rate of change of the first derivative, very negative, a little bit less negative, a little bit less negative. The second derivative is positive, okay, throughout here, but the rate of change, well, not quite the same thing, but what the headline says, the stocks are increasing, meaning first derivative is positive, but the rate of change is slows. That means that the second derivative is negative. That would be how you would rephrase that. The first derivative of the stock prices is positive, but the second derivative is negative. Okay? Because the rate at which the first derivative is changing, which is the second derivative, time rate of change of that. So let's make sure they've got it right in the back. 3.5. The first derivative of the stock prices must be positive, while the second derivative must be negative because the rate of the change is decreasing. Slowly. Okay. Number 2, and they said draw a possible graph. I would suggest something that looks like this. Well, let's start them like this. Okay? You see the first derivative is positive, but the rate of its change is negative. Okay? Number 2, true or false. The third derivative of position with respect to time is 0 for an object falling to earth under the influence of gravity. The third derivative of position with respect to time is 0 for an object falling to earth under the influence due to gravity.
That's incorrect. It would be negative 9.8, like the problem that we did.
Except that was second derivative.
Okay, so it would be 0.
Why?
Because the derivative of the negative 9.8 would be 0. The third derivative, so the derivative after that.
Right. Derivative of a constant is 0.
Exactly. Yeah.
Perfect. 9.8 would be the second derivative, constant, so the third derivative would be 0. Absolutely. Let's make sure they got it right in the back. True. That's all they said. They didn't give why. Okay. Now, number 3. Which type of polynomial satisfies this? F triple prime of x is equal to 0 for all x. Which type of polynomial satisfies that. Basically, almost just answered it. The third derivative is 0. Which type of polynomial? Name some different types of polynomials.
X squared plus.
What would you call that?
Parabola.
Okay, that would be the shape. The quadratic would. It would be a quadratic polynomial. You have constant polynomials, linear polynomials, quadratic polynomials, cubic polynomials, quartic polynomials, quintic polynomials. Which type would F triple prime always be 0 for all values of x?
Or linear.
Linear for sure.
And then also quadratic.
Also quadratic. We just did one like that because the third derivative would be 0.
Right.
So anything quadratic or less, degree 2 or less.
Right. So cubic would be.
Cubic would be a constant.
Okay. Or yeah, it would end up with that. Got it.
Yeah. Okay. So all quadratic polynomials is all they said, but I would say all polynomials degree in 2 or less. Okay. All right. Number 4. What is the millionth derivative of f of x equal e to the x?
Is that really what it says?
That's exactly what it says.
Mine said, when you said that, I was like, are you being sorry? Because mine literally says, what is the 6th derivative of f of x equals x to the 6th? I was like,
oh no, this is
anyway, okay.
f of x equal e to the x. What is the millionth derivative?
Carry the 1, e to the x.
E to the x. Well, I was carrying the 1, huh?
Yeah.
Okay, right. Because e to the x, every derivative is e to the x. Very good. And make sure the back of the book got it right. Good for them.
Yeah,
Okay.
yours is so much more entertaining. Mine was just kind of bland.
All right. Homework exercises here. I've assigned some of these before, but I'll get them all now. Any of the odds 1 through 15. It's calculate second and third derivatives. Any of the odds 17 through 25. And they give you a variety of derivatives there, which, by the way, you still have to do first, second, third, all up to whatever. Then do 27, either 27 or 29 or both, up to you. Any of the odds 31 to 35. Any of the odds 37 to 37 to 51. Okay? I would do some of each of the types there, though. Okay? Further insights and challenges. Do you have a number 52 there?
Yes.
Is it find the 100th derivative
Yes,
of?
now that is, yeah.
Okay. And then the next one's the 99th derivative. Okay, never mind. Okay. We're not going to do any of those. I just always look at those to see if there might be a potential paper topic there, but I don't see any.
Real quick, I
Yeah.
was just going to ask. This week's unaffected, but next week that's our spring break, correct?
You're right, I think, isn't it? I think it's the last week. It's the last week, I believe. It's on the syllabus and it's also on the academic calendar.
And I don't know why we wait so late for spring break.
I've heard some justifications to it.
We were like the latest, some of the latest schools to go.
Yeah. It seems like some of the school systems did it, and that's why we did it. I don't know if it's the county, the city, somebody did it the last week, and then we followed suit.
Because the city goes next week.
Oh, they are.
Well, I know right now, Alabama, they're on spring break.
Right,
this
right.
And
week.
you and me go next week, right?
I think so. I think that's what I've heard.
Because they go before us.
Right. And it used to be the school systems were a bit more coordinated. And I'm not saying this is either good or bad, but I think what it used to be AEA, I don't know if y'all are familiar with that. Alabama Education Association was a very powerful force and lobby in the state, and they plan to have their, I guess it's annual meeting or at least their spring meeting at a certain time, and all the school systems then did their spring breaks at that time so their teachers could go to the AEA meetings. Now, I don't know if this is a measure, I don't know if AEA has quit having the meetings or they've lost influence, or I don't know. I don't know what the deal is. But now it seems like everybody does whatever they want to. And I don't know what governs it. Some places it's Easter, and I know Easter is later this year, but it's not that late. So I don't know if that is tied to it or not. I grew up south of Augusta, Georgia. I don't know if y'all are into sports very much, but what happens in Augusta, Georgia in the spring?
Is that Mardi Gras? No, it's it's the big parade, isn't it? The biggest parade, no?
You're thinking Mardi Gras, that would be Mobile and New Orleans. In fact, one of the community colleges that's down in Mobile, they have to shut down during Mardi Gras because you can't get to campus. They block the route to campus for the route of Mardi Gras. But the Masters Golf Tournament is sometime in April. So in Augusta, Georgia, and Richmond County, Georgia, and even some of the surrounding counties, they always have their spring break week during Masters Week. We don't have anything like that, so evidently I don't know. I don't know why Birmingham and Jefferson County can't communicate better or decide better or something. In fact, why can't we be on just one school system? That would make the most sense to me. But politically, they're not going to do that. All right. I think we're ready then to go to example, to section 3.6. Done enough politicking for now. Okay. Oh. Okay. Now, we can use rules developed so far to differentiate functions involving powers of x, but we cannot yet handle trigonometric functions. What is missing are the formulas for the derivatives of sine and cosine. Fortunately, their derivatives are simple. Each is the derivative of the other up to a sine. And here's a little convention that we use in calculus. Angles are always measured in radians. In calculus, we measure them in radians unless they're indicated as degrees. So always assume you're dealing with radians. Now, before we launch into what we're about to launch into, I wanted you to remind me of something we've already done. Do you remember when we said what the limit as, I don't remember how we said it, let's do h is approaching 0 of sine of x sine of h over h. Let's just do that. Do you remember what that is?
Is it
one of those limits we did back in chapter 2.
Remember our students do. That's 0 over 0, but
yeah, it's an indeterminate form. Now,
I remember our students too.
okay, let me see if this jogs you at all. The sine function starts at 0 and goes like this, right? Okay, and it continues like this. The h goes like this. So basically, they're almost on top of each other. What's the? It's 1.
Okay.
Yeah, this limit is 1. That was one of the biggies we did. I'm just going to go to the end of chapter 2. I bet you it's there.
Doing that, though.
Well, yeah. I think it's 2.6, yes, for sure, 2.6. It's their theorem 2, page 90 in my book. It may be a little off in yours. The limit, as they use theta, I used h.
Sine theta
Over theta is 1.
Yeah.
And the limit, here's the second one.
Yeah.
The limit,
Because, if you want
theta,
to-
let's, yeah, we go back to theta. Theta is approaching 0 of 1 minus cosine theta over theta is
Equal to 0.
0. That one's 0. The other one's 1. Okay? So, now, what we're doing now is the derivative of sine. Okay? And what is our definition of derivative of sine? The limit. We're going back to limits. I know you wanted to.
So, I mean,
As h is approaching 0 of sine of x plus h minus sine of x over h. Right? That would be our definition of the first derivative. This would be the definition d by dx of sine x. Okay? That's the definition. Now, how are we going to do this? Do you remember the sign of a sum rule? One of our trig functions. I can't remember where in this book they put them. I think it's on the front of the book. The front, there's a blank page, and then there's a page in algebra. Do you have that? And then the page in trigonometry. Okay, look at the trig thing, addition and subtraction formulas. Sine of x plus a, x plus y,
yes.
that's it. And what would that be then?
Sine of x
Sine of x,
times the cosine of y
cosine of, except now we're doing h, cosine of h,
plus cosine of h
cosine of h,
times x.
sine of, no, I think that's cosine x, sine of h, right?
Yeah, that's right.
Okay,
Sorry. Yeah.
no problem. If I could get my eraser to come out. I shouldn't be listening to you, should I? Okay, you lead me astray. Cosine x sine h minus sine x over h. Now, I left off the limit thing, but that's what we've got. Okay, now here's the trick. Okay, what we want to do here is to, you see, the limit, well, I'm going to put it back in, as h approaches 0 of that thing. Well, guess what? X has nothing to do with h approaching 0. Okay? So sine x and cosine x have nothing to do with it. So if we can separate out get the h's together and the x's together and pull out the x's outside the limit and only deal with the others. So let's see what we can do here. Okay. Limit as h approaches 0 of sine x cosine h over h plus cosine x sine h over h minus sine x over h, right? Well, this one has cosine x only, and these two have sine x on them. So let's put those into two different limits. The limit as h approaches 0 of, we'll do, give me a color. Blue. Light or dark? Light. Okay. Let's do this one first. Okay. So that would be, the cosine x can come outside. Cosine x times sine h over h. Right? And then we'll do minus.
Okay.
Uh-oh, you're cheating. You're looking ahead, aren't you?
No, well, I noticed something.
Sine x, pull that out of these two. What color you want that one?
How about red?
Red. Okay, I'll do that red. Okay. We'll pull the sine x's out of those two. I'm going to flip the order as well. So that'll be sine x times the limit as h approaches 0 of, pull that out, a minus that, so that's going to be 1 minus cosine h over h. Okay? Isn't it though?
Yes. I did not realize that you could do that you could pull out the cosine x,
If there's no h dependent, the h is the only thing approaching 0. So this goes to 1, and this goes to, I should have it in, that goes to 0. So what do you left with? Cosine x. So the derivative of sine x is cosine x. Okay? Yeah. And you could go back and do the same thing for derivative of cosine x. It's not going to be that bad. You want to go on and do it? Sure. Just for fun. It's so much fun, huh? Okay. So let me erase all that. Okay. And let's do, I'm going to start back with dark again. Okay. Derivative with respect to x of cosine x dx be the limit. You tell me.
As h equals 0.
Of
Cosine parentheses x plus h, or minus h.
okay.
Yep. Minus cosine.
Wait, no, you're right. It was a plus there. This is a minus. Okay.
Cosine x over h.
Okay. Go back to the front, huh?
Yeah. Cosine x, cosine h, minus sine x, sine h.
Okay.
Over.
And you still got minus cosine x all over h. Okay. Now again, we're going to piece together these two and leave that one separate. Okay. That's going to be the limit as h approaches 0. And you want the same two colors again?
Sure.
Okay. Which one you want to be blue?
How about the cosine?
The cosines, okay. That'll be, and let's take out the cosine x from there. Only we're going,
Take a negative cosine x out as well.
why not? Okay. And that will leave us,
Well, no, that's what I was asking is, are we taking out a positive and negative cosine x?
we're taking out the negative.
Just the
Yeah, negative. So that makes the 1 be positive minus cosine h here. I wish I hadn't erased the others, because that was our form, wasn't it? Yeah. Okay. Over h. Okay. And then we'll pull out on the next one.
Negative sine x.
And you want these in red? Okay. Sine x. I thought I went to red. It didn't take. Still not take. There it goes. Sine x times the limit as h approaches 0 of
Sine h over h.
sine h over h. And that goes, this goes to 0, this goes to 1. And so derivative of cosine x is equal to minus sine x. Done. Okay? You don't ever have to do it again. Okay? You got it. Derivative of cosine is negative sine, derivative of sine is positive cosine. They just are each other. And frankly, I like to think in terms of the graphs. Okay? How does, let me go back to black, dark anyway. If this is sine, right? Its derivative is positive to begin with, right? And positive, positive, positive. And by the way, if you remember, that was a positive 1. So I'm going to do the derivative in what color? Green, okay? So it's 1, okay? But it's decreasing until its derivative here becomes 0, okay? And then its derivative here is, if that's a plus 1 there, that looks like a minus 1 here. So guess what we've got here? The cosine curve. And if we did the same thing here, this is starting at 0, but then it's negative. So that's why derivative is minus sine. It really is. If you remember the graphs, you can almost see that they've got to be this way. Derivative of sine is cosine, derivative of cosine is minus sine. Because it starts doing this, goes to negative 1 here, and then goes up to 0 there, you know. So it's the minus sine curve. Okay.
I like the fact that, what is it? Is it every fourth derivative?
Right.
You get back to your original position.
Right.
I think that's so cool.
Yeah.
How it was, I think, on one of the questions during the
Right.
tournament or whatever, but it's just cool.
It is. And we'll probably hit it soon here too. All right, so let's go to example 1. I don't think there's a slide, but so let's just clear the stuff off of this slide. Okay. And okay. Example 1. Calculate, let me go back to dark. It's not quite black, it's very dark blue. F double prime of x, where f of x, this is one of your favorites, is equal to x cosine x. What rule do we use?
That's the
Product rule.
Yes.
And how does the product rule go? We're first going to do a first derivative.
So the first times the derivative of the second.
Okay, that'd be x times
Sine x, or negative sine
negative sine x
plus derivative of the second, so cosine x times derivative of the first, which is just 1.
1. Okay, got it. So let me write that again, and let me write it this way. Cosine x minus x sine x. Okay? What would be f double prime then? Let's use that one there.
So cosine x, looking for the, okay. So, yeah, would you just go ahead and bring down the cosine x?
Nope. You take the derivative of it.
Okay, so negative sine x.
Negative sine x
So negative x times cosine x.
cosine x
And then, so sine x
minus sine x.
minus sine x, yeah.
Because you already had a minus sign in front.
Right.
So what do we have here then?
So negative 2 sine x minus x cosine x.
Now it's a little early to determine a pattern
I'm
here.
looking for it.
So you'd have to do a few more, but it looks like it could be, you flip the function back and forth, and stuff, and it started with the first derivative being a 1 cosine here with x times the opposite, and then this, so you'd have to do a couple more.
Yeah, I would need 1 or 2 more.
What's that?
I'm kind of,
To find independent.
Yeah, you're going to have to do at least 2 more.
Yeah.
I think maybe you could find it then, but it looks like it might be emerging. No promises though. Okay. But I think you got them right. Okay. Now, the next is what we've already done basically. Ooh, maybe not. Oh, that was bizarre. Okay, sorry about this. I neglected the fact they were going to do some of the same proof that we did. So the next couple slides are
the
basically,
stuff that we did.
yeah, on the previous one. That derivative of, now pretend we didn't do example 1 yet. This is going back to the proof of the other. Here's how we started. d by dx of sine x was the limit as h approaches 0 of sine of x plus h minus sine x over h. Exactly like we did. And then they expanded it, and they didn't show, in the book they show the expansion. Here they don't. Okay? They jump right to the end here. Oh, they do. Look, I'm sorry. They show a whole bunch of it. Okay? I thought they were just going to show the last line of it. So they start with, they lift off the limit for now. Sine of x plus h minus sine of x of this would be sine of x cosine h. Oh boy. They skipped a bunch of steps, okay? It's supposed to be sine x cosine h plus cosine x sine h minus sine x, and then they rearrange and get the h's together, cosine h's together, and sine h's together, both over that, and so then they go back and put the limits in, with a strange way to do this. Why didn't they leave the limits in? Save them stuff here. And then what they can do, because the limit is only dealing with the h's, terms without h's are not affected by the limit, so you can pull them outside the limit. So the thing you said you didn't, and that, by the way, equals 0. We did it the other way, and that's why I flipped them, but if it's the other way and this way, either way, it is 0. But this one, pulling the cosine out, that is the limit is 1. So that gives you derivative from sine x is cosine x. So the first term goes to 0. And then here is the graphical insight, which is basically what I already did too, at least to a small extent. Okay? They're only lining up the zeros. Okay? If this is, the blue is the sine curve, they picked out the places where the derivative of the sine was 0. There, there, there. Now they didn't say it, but this appears to be at least right there in a limited domain. That looks like the identity function. F of x equal x, right? That looks like the line that bisects here. So it would have a slope of 1. So put that as 1. If that indeed was 1, this would be like a minus 1, so there would be a minus 1. This indeed would be a 1 again, so that would be a 1 here. This would be a minus 1 here, so minus 1 there. So sure enough, 1 plus. The y is equal to sine x. When you plot its derivative, you get a function that looks just like the cosine function. Because it is the cosine function, okay? And sure enough, that seems to work. Seems like their pattern here is to have the basic functions in blue and the first derivatives in magenta or pink or whatever you want to call it. Okay. Here's the next theorem. Okay, we did sine and cosine. Well, how in the world are we going to get these others? I don't know if, say again?
I was just going to say with sine and cosine, you can just manipulate those formulas to get
Yes.
like tangent and then
Exactly.
tangent, blah, blah, blah.
Okay, because you know that you already hit on it, that tangent x is equal to sine x over cosine x. So the derivative of tangent x would be the derivative of the quotient, which frankly I would rather do derivative because I don't like quotient rule as much as I do. It's fine, there's nothing wrong with it. But I would write this as sine x cosine to the minus 1x and use a product rule because I like product rule better. Okay, I don't have to remember high d lows and low d highs and all that kind of stuff. Okay, so what would that be? And you love the product rule, I know. So what would that be?
So sine x
Sine x.
and that's that just sine, another sine x.
Okay, it's in there. You have a minus cosine to the minus 2, so that would be a cosine squared x times another sine x. Here's the problem with doing it this way. You have to know chain rule, and we haven't done chain rule, so let's back up and do it the other way. Quotient rule, yuck. Okay, so let me go back and erase. I forgot. With the product rule, you need, in this case, you need the sine rule. So this will be, okay, what is the quotient rule? Remember what the quotient rule is? How does it start? You start low.
Yeah, okay, low d high, high.
Okay, low. Low is
So
cosine x.
Low d high. Okay, so derivative of sine x is just cosine x again.
Okay, so that's cosine squared x
Okay. Low d high, so sine x
minus
minus, that's right,
sine x.
sine x. And then sine x again.
Right, only it's minus sine x.
Right,
So it'd be plus sine squared x
right.
over
Low squared, so cosine x squared.
cosine squared x. Okay? Any idea what cosine squared x, what sine squared x is?
Is that 1?
Yes, it is 1.
I remember that being one of the,
It's a Pythagorean identity.
right.
And what's 1 over cosine squared x?
Uh,
1 over cosine is?
Sine, no, is that 1 over cosine? Is that sine?
Uh,
No. Cosecant?
not cosecant, secant.
Secant, that's right.
This is secant squared x.
Okay, cool.
And there's where you get derivative of tangent of secant squared.
That's it. Okay.
Okay.
Yeah.
Now, you could go through the same process again with cotangent, which is cosine over sine, and it'll also wind up cosecant squared, but it'll be a minus.
Okay.
The reason for that is that just flip those around some and you get, well, you could work it out. You'll see you'll get a minus 1 on the numerator, and then cosine, or secant, or sine squared on the denominator, and that would be minus cosecant squared. Now, secant x. Tell me what secant x is again. Let's see, I don't think they proved this one. I think there's a reason for it. Okay. How are we doing? Okay, we got time. Okay, let's do secant. D by dx of secant x. And what is secant x, by the way?
1 over cosine.
Okay, d by dx of 1 over cosine x. Okay, now, again, we'll use quotient rule, so that would be what?
Cosine x. And that's 0. Yeah.
Yeah.
And then minus 1 sine x.
Only minus sign.
Minus sine, right.
So that's will make it.
Into a positive, right.
Okay.
Over cosine squared x.
Got it. Okay. Now, you would think, why did he write the 1 down there? Most of the time, he doesn't. I don't. But here's why I wrote it down now. You can split this as 1 over cosine x times sine x over cosine x. What's 1 over cosine x?
That's secant x.
Secant x.
And tangent x. Oh my, that's cool.
And there it is.
Nice.
So derivative of secant x has secant x in it, but not just secant x times tangent x.
Oh.
Okay? And then for the cosecant, by the way, so same as you would expect, except with a minus sign. So if you combine those two with our first two, d by dx of sine x, what was that?
Sine x. Cosine.
Cosine x.
Yeah.
And d by dx of cosine x
Sine x.
and
Negative sine x.
negative sine x. Now, just a little thing, it helps me. I don't know if it helps you or not. Notice for the cofunctions, derivatives are always negative.
Negative. Oh, okay.
And the ones without the co in them, they're positive.
Huh.
Okay. I don't know. I just remember that.
Yeah.
Okay. And later in this chapter, I think, we're going to get hyperbolic functions, and there are the signs. To me, I had, Mr. Racy. Do you know Mr. Racy too?
Absolutely.
You did? Okay. She and I had a pretty big discussion Friday on whether to cover hyperbolics or not. She said, oh, yeah, cover them. I said, I'd never use them except here, Well, they use them in some type of engineering. I said, well, what kind? Well, they use them in some kind because blah, blah, blah. I said, okay, if you want to cover them, cover them. But frankly, the sign conventions and the other things are just enough off that I have to go back and redo them anyway to make sure I've got them right. Or I'll look them up. So if I'm looking them up, why memorize them? So I say don't, but she's going to have her class do them. More power. Okay, fantastic. Go for it. So let's do example 2. We've gotten these. Let's do example 2. Yeah, I think there is a slide, so we'll do it here. Verify the formula.
We just did that.
We just did it.
Yeah.
Okay, so we've just done it. What they say, though, is then look at your graphs and see what you get there. Okay? Well, here is a tangent function. It goes, remember, as a vertical asymptote at all the half pi's, they only drew one in, but there's another one there and another one there. Okay? And its derivative, if you haven't guessed it yet, that looks like a 1 there. The slope there looks like a 1, and sure enough it is. Here the derivatives are positive, being extremely large positive slopes, but then decreasing until they get to 1. Sure enough, same vertical asymptote here, and there. Okay?
That's cool.
More so, remember that this is secant squared, so these go even higher. Okay? And secant would have come down here next, but since you're squaring it, it's up there also, and it just repeats the process over and over. And same thing up here, the slopes are just a little bit greater than y, going to infinity. So sure enough, that looks like it fits.
I like how it shifts from a cubic to a parabolic function. You assume, or
Kind of like a parabolic.
Yeah.
Yeah.
I like that though.
Yeah. It's actually parabolic and secant, but yeah, it's the secant function itself looks a little like this. It just flattens it out more here.
Right.
Yeah. Okay, so there was example 2 we've already done. So let's move on to example 3, which looks like we have a graph for it too. Find the tangent line. Oh, we got to remember what our tangent line formulas are. To the graph of y is equal to tangent theta secant theta at theta equal 4 pi fourths. I don't know why I said 4 pi fourths. Okay? Now, the first thing to think about here, and it really should bring little warm fuzzies to your thought process, is that couldn't have been a pi halves, could it?
Right.
Because tangent and secant both are not defined there. They are defined at pi fourths if you just think of how their functions just look, so we can do that, okay? So, it said find the slope, the tangent line, find the tangent line. What are we going to need to know the tangent line?
Derivative.
Yes. So y prime, and guess what rule we use? Product rule, and how does that go?
Derivative, let's see, first times derivative, second, so tangent, theta, secant x, tan x.
Secant theta, tangent theta.
Sorry, yeah, tan theta.
Okay.
And then second, so secant theta.
Plus
secant theta.
secant squared theta. Oh, you're doing, okay, got it. Wait, okay, I got it. I understand what you're doing now. Okay. Second times derivative of the first, okay.
And then tan is secant squared theta.
Okay. Done. And what does this come out being?
Tan theta, secant theta.
Tan squared theta.
You're right, tan squared.
Secant theta plus cube. Secant cube theta. Secant times secant squared is secant cubed.
Okay, sorry,
X times x squared is x cubed.
on right where you're distributing the tan theta. Why did
I'm not distributing, I'm just multiplying.
Oh, you're just okay. So you just
those two together
got
becomes this one
sorry.
plus
Got it.
secant cubed.
I was just hung up on the first part. I'm sorry.
Now, if you were distributing, you could factor out a secant
Right.
out of both of those and leave you a tangent square plus, and that might not be a bad idea. I don't think it'll get you anything, but
It's okay.
Yeah.
Like I said, I was just a little hung up, but you're good. You're fine.
Yeah. Okay. Now, that's what y prime is. Okay? That's one thing we need to get a tangent line. What else do we need? What does a tangent line tell you? Slope, yeah, exactly. The slope of the curve, and all we need is a point. Okay. So we need a point, and we need the slope at that point. So here's your theta. So your point is going to be theta y. Okay, that's your point. We already got the theta part. That's pi fourths.
So now we just got to plug it in.
Plug it in there.
Right. Original.
Okay.
So
Tangent pi fourths. Oh. Oh. You're going to kick yourself. If not, I'll kick you.
Is it going to be roll? Is it 1?
1. Tangent of pi fourths is 1. Now, secant is, go back to sine and cosine.
Okay, so 1 over cosine.
1 over cosine. What's cosine of pi fourths? What's that? You have 1/4? Oh, okay. That happens to be, you got, yeah, you're doing secant of, or 1 over cosine of pi fourths. It is, okay, cosine of pi fourths is square root of 2 over 2, which, by the way, is 1 over root 2. So secant would be root 2, which is 1.414. So you're absolutely right. So this would be root 2. So this thing is root 2. 1 times root 2 is root 2. Okay, so there's your point. Let's take this value and plug it in here. Y prime, which is also m at theta equal pi fourths.
That still be 1.
Okay, the tangent will be 1.
And
Root 2 plus
root 2. Or no?
cubed would be 2 root 2.
Okay.
Because squared would be 2, and then another one would be, yeah.
Cool.
So this is, pull out a root 2.
Is that 3 root 2? Or?
3, yeah, you got it. This is 3 root 2. Okay. So now you got point and a slope. Can you come up with a tangent line?
Would you put it in point slope?
Absolutely. Well, you got a point and slope. That'll work. What will that be?
So y equals
Y.
y1 minus y2.
Well, y minus y1, which is
We get 3 root. Okay, so root 2.
y minus root 2 is equal to 3 root 2. There's your slope, right? That's the slope. Times x minus pi over 4.
Got it.
Okay? Looks a little messy, but add a root 2 to both sides. Ew. Okay? And this would be y is equal to 3 root 2x plus that other mess. Huh?
So how would you write down?
Actually, leaving it in that last form is just about as good as anything. But if you did this,
2 times pi over 4,
yeah,
times pi.
minus 3 pi root 2 over 4. Why not? I mean, that's all it would come up being.
And then plus pi.
No. Oh, yeah, I forgot that. Plus root 2.
Yeah.
Okay. So now that would be 3 root 2x put plus root 2 times 1 minus 3 pi fourths. Okay, right? Okay, which would be 3 root 2x plus root 2 times 3 pi over 4. It's a mess. Let's see how they left the answer. They left it, like I said, they left it in this form right here.
Okay.
They didn't do anything else. They said y minus root 2 is equal to 3 root 2 times pi minus. I have x in there. Phew. It's theta. Again, I was listening to you, I think. Okay. Theta minus pi fourths.
Real quick, how did you, in the parentheses at the bottom,
Yeah.
you go from 1 minus 3 pi over 4?
Yeah.
How did you get the positive 3 pi over 4 on the right hand side?
Oh, I'm sorry. This was a 3 here. My scratching, I didn't see. That should just be pi fourths. 1 minus 3/4 pi is, this is 4/4 pi. Wait, no, that's not right either. Forget that.
Okay.
It was a mess. Okay. Oh, well, no. No. 1 minus 3/4 pi would be 1/4 pi. Wait, no. This would be 9.
I see what you're saying.
Yeah, no.
I see exactly what you're saying.
Pi,
Yeah.
4 pi over 4. Yeah. This is 4 pi over 4
Got
pi. But it's 4 pi over 4 pi. So it doesn't.
Yeah, no, that makes sense. I wasn't.
I was trying to do something I couldn't do. Okay. Yeah. Okay. They left it in that form, which is a perfectly good equation of a line. It's just not slope-intercept form. Okay. That finishes 3.6. Woo, goodness. Could I have timed it any better? Isn't 11:10 on the nose? Oh my goodness. So do you want to do your preliminary questions at home or do those when we come back next time? Okay, we'll start there. Homework exercises then will be either 1 or 3 or both. Any of the odds 5 through 23. Any of the odds 25 through 33. Either 35 or 37 or both. Either 39 or 41 or both. Any of the odds 43 through 51. And I would do some of those easier ones and some that maybe aren't quite so easy. And then let's just look at further insights and challenges. I don't see anything really big there. So we'll start next time on, we'll do the preliminary questions and then we'll go to the chain. Chain rule's fun. It's a good thing to do. Huh? What's that? Yeah, I do too. Yeah, that's why I said it's fun. All right, good deal.